In this section, we're going to be talking about AC circuits. What we mean by this, AC is alternating current. The current alternates because of an alternating voltage source. So alternating voltage source and alternating EMF. So what we're saying by this is that the voltage or EMF supplied to the circuit is alternating with time. Now, it's alternating sinusoidally, meaning we could write it as a sine function or a cosine function. Let's just go ahead and say a cosine function, which of course just means that at time equals 0, we would measure a maximum value of that source voltage. So we would say that this EMF that is supplied to the circuit is equal to a maximum value, so that EMF naught times the cosine of omega t. Value changing. This epsilon naught represents the maximum value of the EMF. If you remember any sine or cosine function, that's the amplitude. So the maximum value of that source voltage that is supplied to the circuit. Omega is the angular frequency. Omega we can relate to 2 pi f. So f frequency being the rate at which, how many oscillations per second that this source voltage makes. So our wall outlets are 120 volts at 60 hertz. So our regular wall outlets, this 120 volts is what is called an RMS value. So we would represent that as the EMF RMS. RMS stands for root mean square. 60 hertz is the frequency of our source voltage. So how many oscillations per second or cycles per second the source voltage oscillates at. So here, let's talk about root mean square. We talked about it briefly in terms of electric field and magnetic field when we were talking about electromagnetic waves. The purpose of ERMS is to talk about kind of an average. When we look at a sine or cosine function, the true average of this cosine function for this voltage would be 0. But that would imply that on average we're getting nothing from the wall outlet, which of course doesn't make any sense. We can plug any of our appliances into the wall outlet and charge them or get them to work. Whenever we relate to the wall outlet and the energy, we're always relating to a squared value. So for example, if we're talking about a resistor, the power dissipated or converted in a resistor would be the potential difference it experiences or has at any given moment, that potential difference squared over R. So if we think about a voltage squared, we're taking this function, even though this is the battery, we still are representing this similar concept. When we square the function, everything becomes positive. And so squaring looks like this. So just taking our function, squaring both sides. Once we square both sides, if we want to find the average E squared value, EMF squared value, then we're looking at the average value of the cosine squared function. That is 1/2. If we take the square root of both sides, this is what we call ERMS or EMF RMS. Square root of both sides. I'm going to go ahead. The square root of the maximum value squared is just going to be the maximum value. And then we'll end up with the square root of 2 on the bottom. When we have an oscillating source voltage, we also end up with a current through the circuit that will oscillate with time. And we could go through a similar process to show that the RMS current will equal the maximum value over the square root of 2. So you can think of this RMS value as an average of sorts. So when you look at our outlets here, and we say that it is a 120 volt outlet at 60 hertz, the 120 volts is this RMS value. It is not a peak value. We can certainly find the peak value. The peak value, just using our relationship below, we would multiply by the square root of 2. So the peak value of the voltage our wall outlet supplies, I believe that's around 170. Let me see. Square root of 2. Yeah, so 170 volts. So if we were to graph our source voltage as time goes on, we would see the amplitude. If I come back over to my original graph, for our wall outlet, the amplitude would be 170 volts. That would be what's supplying to whatever device we perhaps may plug into the wall. In a circuit, we're going to represent an alternating source as a circle with a little sine or cosine curve in the circle. So if you recall, a battery was represented by a long line and short line, or even a couple long and short lines, where the long end of the battery represented the higher potential end. The short end of the battery represented the lower potential, so the smaller voltage. So an AC source, an alternating source voltage, will be represented as a circle with a little curve inside. We will be looking at how a resistor by itself acts or responds in a circuit, how a capacitor alone would respond, how an inductor alone will respond, and we will be looking at just very basic series circuits. So for those of you who perhaps may have taken some EE courses, electrical engineering, you will be familiar with this. We're going to be very basic though, so don't make it too hard, essentially. One other concept though to talk about before we start talking about a resistor or a capacitor is a concept called a phasor. When we have these alternating source voltages, so I'm just going to draw my graph again. And again, we're going to go ahead and just assume a nice cosine so we don't have an initial phase shift. When we start putting a resistor and a capacitor and an inductor together, it turns out to kind of easily do this, we need to use what is called a phasor. A phasor is essentially a vector that rotates So, for example, we put this system, the length of the phasor. So I would draw a vector. The length of this vector represents the maximum value of whatever I'm representing. So in the case of looking at our function representing our source voltage, the length of this would represent the peak value of the source voltage. So the maximum value that source voltage ever reaches. Now the purpose of the phasor is to help us visualize the value of the voltage at any given moment in time. The way we do that, if you think vectors in general, vectors can be written and drawn as having x and y components. So this specific vector I've drawn at this moment in time has an x component that would be this long. And that's based off of the length of the phasor, the maximum voltage, and at this angle in here. This side would be the maximum EMF is the cosine of whatever that angle happens to be. We say that this, because if you recall, we said that we're describing the instantaneous EMF by this cosine function. We said, though, we're saying cosine omega t, but omega t is an angle. Oh, I wrote the same thing again. Okay, let's get this right here. So the angle in my little diagram is omega t. So this horizontal or x component of my phasor represents the instantaneous EMF, the value of the source voltage at that exact moment in time. Okay, so if we wanted to perfectly or estimate roughly, I'm just drawing my EMF function again to represent my EMF as a function of time. If I was to draw my phasor at time equals 0, I know the phasor is the instantaneous value at this moment in time right here is the maximum source voltage. I would draw my phasor pointing directly to the right, which means it is all in the x direction. And so the instantaneous value at this moment is the maximum source voltage. But just a short time later, say this time right here, this could be represented with my original picture. My EMF is still positive at this moment in time. I'll call it at time 2. It is still positive, but it's not a maximum value. So when I look at my phasor, my x component is positive. It's not equal to the maximum EMF, but it is positive. So what has happened between here, time 1, time equals 0, and here, this second picture, is that my phasor has rotated counterclockwise. So when I mentioned initially that a phasor is a vector that rotates, we're essentially saying that this EMF, this vector, is rotating counterclockwise at a rate of omega. We know omega is 2 pi f. So if we think frequency being cycles per second, this phasor is going to go all the way around in however many cycles or circles per second. So our wall outlets, 60 hertz. That means 60 cycles per second, 60 circles per second. Now that's really fast, of course, and it's not like we need to sit here and watch this happen, but the phasor allows us to say, hey, let's take a picture at one moment in time, and we can represent it by a phasor. So for example, coming back up to my graph, let's say we wanted to talk about this moment in time. Yes, really, I should do a dot. So there's a certain moment in time here. I know the EMF, the instantaneous value of the EMF is negative. And at one short, but let's say it this way. It's negative at this moment, but it's getting closer to 0, or it will be getting closer to 0. So my phasor, just draw myself a little coordinate system to represent a negative EMF, but that is not a maximum value. I have two options. My maximum EMF could be pointing in the second quadrant there, or it could be pointing in this third quadrant. Either way, both of these would have a negative instantaneous value of the EMF. A negative x component of a vector is essentially what we're saying. Now, to decide which one of these is correct, we need to think about how these phasors rotate counterclockwise. So if we were to look even just 1 millisecond later, our phasors will have shifted. This one will have shifted closer to this negative x-axis. The bottom one will have shifted a little bit closer to the negative y-axis. Both of these would still give us a negative EMF. This top one now gives us a larger instantaneous value, well, a more negative EMF at this very short time later. This one's x component is shorter So this one gives us a less negative EMF. Well, coming back to the graph, at a very short time later, we still have a negative value here, but it's closer to 0. This is the one that represents that. So this should be, or will be, the phasor that accurately represents that point in time. So the EMF phasor here matches this point right here. It tells us there is a negative value of the EMF at that instant in time, but because phasors rotate counterclockwise, as this EMF phasor or vector rotates counterclockwise, this x component will be getting smaller. It still will point in the negative x direction for a little bit longer, but it will get smaller as that EMF rotates, that phasor rotates. Now, this might sound completely and totally confusing at the moment. The reason we need to talk about phasors is when we put everything together. Our ultimate goal here is to have a resistor and a capacitor in series to a source voltage that is alternating with time, and a resistor, inductor, and capacitor in series. In order to talk about the circuit as a whole, because a resistor, inductor, and capacitor behave differently, we have to use phasors to pull them together and talk about the behavior of the circuit. If you have had EE classes, we're not going to be getting into the imaginary portions. If you haven't had EE classes, we still aren't going to go there, but that will make no sense to you anyway, so just ignore what I just said in terms of imaginary stuff. So we're going to look at the individual elements connected to the alternating source, talk about equations that describe them, and then put them all together.